last week, close to the end of class, I was kind of talking about naming atoms a little bit. And well, naming atoms in terms of the amount of protons and neutrons that it have. For example, here I have an atom, right? Let's just call it atom X, right? We all know there's a top number and an underneath number to go. The top will be the mass number. That's usually the larger number. And the number underneath, well, that's your proton number or atomic number, which is usually the smaller number. Do you all think for this particular atom, do you think you could send the top value and the underneath value for me quickly? The underneath number, this smaller value, is the amount of protons. I think some of you all are forgetting that. So for this particular atom, it has 1, 2, 3 protons. In case you forgot, protons are the positive ones. So the 3 will go underneath. Now, the top number is the protons. I'll use P for protons and, well, the N for neutrons. The top number is the protons plus the neutrons. So we're basically adding up everything at the center. So 1, 2, 3, 4, 5, 6, 7. For those who got it wrong, well, I hope that refreshes your memory a little bit. Okay, fine. So this element is named X, and its top number is 7, and the underneath number is 3. Now, whenever we are naming an element, whether it's hydrogen or carbon, nitrogen, iron, copper, whatever element it is, its name does not depend on the amount of electrons. Its name basically depends mostly, and I'll clarify that term, mostly on the center, the nucleus. In other words, the protons and the neutrons, but mostly on the protons. You have to keep your eyes on the protons. If the amount of protons change, then the actual name of the element will change. For example, if I were to throw away one of these electrons, so you see this electron here, let's throw him away. Will his name still be X? What do you all think based on what I just said? The answer is yes, it would still be at the end of the day X, but it's just a slight different. It's an X ion, right? Meaning that it's missing an electron, but his name is still X. Let me put that in a different perspective. Carbon, right? Carbon 12, the one that you find on the periodic table. Obviously carbon has protons, neutrons, and electrons. Let's say for carbon, we thief one of the electrons. Like we take one of the electrons and we throw it away. His name will still be carbon 12, the one that you find on the periodic table. You notice his name, carbon, did not change, right? So whether electrons go missing or not, the core name of the element stays the same, right? Now, there's 2 types of carbon, carbon 12 and carbon 14. Carbon 14 is an isotope of carbon. Who can tell me what's the main difference between carbon 12 and carbon 14? What's the main difference? Is it there's a difference in electrons? Is it that there's a difference in protons? Or is it a difference in neutrons? Right. Since these two are isotopes, right? The only difference between them is that carbon 14 has 2 extra neutrons. That's all it has, you know. It has 2 extra neutrons, okay? But even though it has different amount of neutrons, it has the same amount of what? Protons. So because the amount of protons remain the same, and we don't even care about the electrons when we name and stuff, you notice its core name is still carbon. It's just a different type of carbon, but it is still carbon at the end of the day. Now, so in other words, if for this element here, X, if I add more neutrons, I keep just adding neutrons. So now I have 1, 2, 3, 4, 5, 6, 7. If I do that, its underneath number still remains 3. But what would the top number change to now? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It would change from 7 to 10. Do I need to change the letter? Do you think I should change the letter X to a different letter like Y or Z? Do you think that is necessary? The answer is no, because it still has the same amount of protons. When I added the neutrons, I just created an isotope of the original one. It's still X. However, if now I were to add an extra proton, the underneath number will change to what? 4, indicating that there's a change in protons, and the top number will now be 11, because if you add up everything in the center, you have 11. Do I have to change the name now? Is it necessary to change that letter X to a different letter? The answer is yes. No, I have to change the letter X. It doesn't really matter what I change it to. I just have to make sure and change it to a different letter because it's no longer X. It's a totally different element. All right? Which brings us to this top note here. I want everyone to take down the note in red, and essentially everything I just explained is summarized in that note. You're keeping your eyes on the proton. Once the underneath number changes, the smaller number changes, that obviously indicates that the amount of protons has changed. And once that changed, the underneath number, right? We have to change the name of the element. Let me know when you are finished taking down the note. All right, so here we have an element. We just don't know the name of the element right now, right? Let's put in one more. I just want to put 2 more neutrons. Let's just call it X. So just like before, right? The underneath number will be 3. And the top number from, if we count up everything in the center, will be 7. Let's just assume it's radioactive. So this atom is radioactive. And remember, I kind of compared something being radioactive to being sick, and it needs to get rid of some of the stuff inside of it, almost like vomiting, so it would feel what? Better. So let's just say, for simplicity's sake, that this atom decides to shoot out alpha. That's the type of radiation it's giving off. Alpha is actually 2 protons and 2 neutrons. So think about it. If alpha itself, right, is 2 protons and 2 neutrons, its number would be 2 and 4. Everyone okay with that? The 2 represents that it has 2 protons, and the 4 represents the total of protons and neutrons. We okay with that, right? Right. So here's what. X is radioactive. This guy is X. So he decides to shoot out alpha. But alpha, like I said, is 2 protons and 2 neutrons. So the atom gives up how much? 1, 2 protons and 2 neutrons. Well, since it gives off these 2 things, you can pretend that it no longer exists. I have an erase button. I should have used this instead. So it gets rid of 2 protons and 2 neutrons. Can we still call it X? Is this atom still X? The answer is no, clearly no. Because you all notice that it used to have 3 protons, right? But now, because it gives off alpha, it loses 2 protons and 2 neutrons. More importantly, it loses protons. So the amount of protons changes. So we can no longer call it X. So X changes to a different letter. Let's just call it Y, okay? What number will go underneath and what number will go on top now? Look at it now, it changed. The underneath number will be 1 because it only has 1 proton now. And the top number will be what? 3. And to keep it balanced, remember, it just gave out alpha, and alpha is 4, 2. You all notice something? Add up all the top numbers on one side of the equation. Pretend the arrows are equal sign. 3 plus 4 is how much? 7. 1 plus 2 is 3. We're keeping the equation balanced. All the top numbers, when you add it up, have to be equal to the top number on the other side. And the underneath numbers, when you add it up, you have to get the number on the other side as well. So it's a kind of mathematical equation. All right? Right? And alpha is always 2, 4, meaning that alpha will always, always, always be 2 protons and 2 neutrons. That's the definition of what alpha is. It's 2 protons, 2 neutrons moving at a very, very high speed, right? You all notice that before it used to have 3 protons, right? Well, to keep it balanced, if there's only 1 proton now, do you all think we will need 3 electrons? What do you all think? No, most likely the atom is going to what? It's only going to need 1. So most likely it will lose these 2 electrons. They will just go off somewhere else, right? Let's not think. I'm not going to go into detail into it. Just know that the other 2 electrons are not necessary to keep the atom at a neutral charge of 0, which is how the atom wants it. All right? But good question, either way. So beta is a fast-moving electron. So when students hear fast-moving electron, the word that stands out in their head is electron. So we go back up, and whenever you hear the word electron, you automatically think the electron that's circling the atom. I mean, what else would you think of, right? And that is exactly what I used to think of. So you know what I used to think when I was in high school? I thought beta was when one of these electrons it shoots out at a very, very high speed. And I thought that was beta. And how much of you were actually thinking that? Be honest. Like if you had to guess what beta was, you would automatically go to the orbits where the electrons are found, and you just assume one of those shoots out into the atmosphere at a very, very high speed. And you call it beta. Well, let me give you the full story of what beta is. That is not beta at all. the neutron. Remember, at the center of the atom, it have protons, and of course, it have what? Neutrons. Did you ever, now we know the protons are positively charged. We know electrons are negatively charged. And we know neutrons have no charge. Well, it has a neutral charge. Let's investigate what a neutron is. A neutron is when you take an electron, which has a negative charge, and you take a proton, which has a positive charge, and you squeeze them together. And when you squeeze them together, you get a neutron. Because, and the reason a neutron has no charge is because the negative charge cancels out the positive charge. So you can think of a neutron like this. The neutron is like a proton, and like how Pac-Man is eat those ghosts, right? The electron inside of it, the two of them squish together. Now, anything you can squish together as one, you can separate it. So if you want, you could take a neutron and split it up into a proton and an electron. Everyone with me so far? You can either squeeze the electron and proton together to get a neutron, or under certain circumstances, it can split back up into its original form. And that's very, very important, right? And you're going to see why just now, right? You don't have to take down anything there. You're going to hear me say it again. So let's go back. Let's draw an atom again. Let me get this off the recording. So this atom is radioactive. So it needs to get rid of something, right, in order to become stable. So it decides to shoot out beta, right? Now, remember, beta is a fast-moving electron. So right now, the name of this atom would be 2,4. Remember, I'm just making up an example here, right? 2,4. If it shoots out beta, you have to ask yourself where the beta comes from now. One of these neutrons is going to sacrifice themselves. So let's assume it's this neutron. So he sacrifices himself and he splits up into a proton and what? An electron. But you see this electron here? He gets ejected from the atom at a very, very high speed. And because it's an electron moving very, very fast, you call him beta. So you all realize where that fast moving electron comes from. It does not come from the orbits. It does not come from the shells. It actually comes from the nucleus, and more specifically, from a neutron in the nucleus splitting up into a proton and electron. But electrons cannot live in the center. So he gets kicked out. He doesn't even get kicked out to the orbits. He gets kicked out way out, and we call him beta. Question now, can we still call this X? What do you all think? Can we still call this X? The answer is no, because the amount of protons have changed, and the protons is the more important one when we deciding if there's a name change or not. So let's just call him Y. After X, I always use Y. You can use Z if you want, and it's really up to you. The underneath number is now going to be what? 3. But what would the top number be? What would the top? The top number is still 4, because at the end of the day, it still have 1, 2, 3, 4, right? So apparently, beta is 0 minus 1. And I'm going to prove to you that it needs to be minus 1. When we add the top numbers, we notice we get 4. 0 plus 4 is 4. And the other side is what? 4. The underneath, 3 plus minus 1. A plus and a minus is a minus. So 3 minus 1 is 2. At the end of the day, when something emits beta, the top number remains the same. You notice the top number remains the same, but the underneath number increases by 1. Take down this, right? And we're going to get a lot of practice in a little while. So at the end of the day, alpha is something physical. Well, when something emits alpha, let me go up here a little bit. Remember, alpha is something physical. You can hold it, but if your hands were small enough, you could hold it, okay? Alpha is 2 protons and 2 neutrons just moving very, very fast. Beta is still something physical. Beta is a fast-moving electron. So if your hands were small enough, I guess you could grab an electron, a fast-moving electron. But gamma, he's well, even though he's like the strangest one out of them, for me, he's the easiest one to explain. Gamma, as you all remember, is not a physical particle. It's pure energy. So let's say we have a radioactive atom. So we'll put 3 protons and 2 neutrons, right? And we all know to balance it off, it needs to have 3 electrons, right? 1, 2, 3, 1, 2, 3. So gamma, let's say he's radioactive. Now, the only way, well, one of the ways you can get gamma is when the core itself, the nucleus, has too much energy. In physics, we call that an excited atom. We say the atom is excited. And to depict that it is excited, like it has too much energy, like you give someone too much sugar to eat, you just put a little asterisk next to it. So in other words, if this is X, the underneath number will be 3, and the top number will be what? We use a different color here. I think that's hard to see. Let's use white. The underneath number will be 3, and the top number will be 5. So now it decides to shoot out gamma. Since gamma is not a physical particle, it's not a proton, it's not a neutron, it's not an electron, do you all think it's fair to still call it X? Because when it shoots out the gamma, it's not going to change the amount of protons. What do you all think? Should I call it X or should I change it to a different letter now? It should remain X, right? Its name will still be the same, right? Because when it shoots out gamma, none of the particles actually change. It's just the amount of energy within the nucleus gets less. But having less energy doesn't mean the amount of protons changed. So it will still remain 5 and 3. And gamma is actually 0 on top and 0 underneath, which makes sense because as a gamma has no protons, no neutrons, no electrons. But how do you know? But there is a slight difference between these two X's. One has too much energy, and when it gives off the gamma, the atom itself has less energy. So the one that has too much energy, you just put an asterisk next to it to show that, hey, that one had too much energy. So at that point in time, it was radioactive. And after it shoots out the gamma, you notice the asterisk is no longer there, meaning that it has lost enough energy and it's no longer radioactive. So that is what makes gamma so easy to explain and calculate. The top numbers remain the same, the underneath numbers remain the same. The only difference is the asterisk. Even the name of the element remains the same. Right, so take down that one, and then we're going to do some practice questions. Whenever they're writing alpha, beta, and gamma, they just have slightly different symbols, okay? Let's get to alpha, right? Remember, here is no alpha because you could use the symbol alpha. And of course, it is no alpha because it has a 4 and a 2. Sometimes for alpha, it is used He, which is helium, but it has a 4 and a 2. So these two things are the same thing, right? So once you see the 4 on top and the 2 underneath, it's the same exact thing as alpha, right? So you don't have to take it down. You'll be seeing it over and over today. For beta, most of the times they use this symbol, or they'll use the letter E, which is 0 and -1. The point is that I have a 0 on top and a -1 underneath. So you know beta from a mile away. So let's try some questions here. Now I went online and I found a little worksheet here. All right. Let me zoom in a little bit. It could look a little, I say, intimidating. Look at question 1, right? They're asking you, I'm working out the first few for you. Simple 1-mark questions in the exam, real simple. Here you have uranium, right? And apparently this is a radioactive type of uranium. What kind of radiation is it given out? Alpha, beta, or gamma? You don't have to write it down. Let's answer on the chat. Which one is it? Obviously, it's alpha. Because you see He, and don't get me wrong, they could have just used the alpha symbol, but 42He is the same thing as alpha. And you all will notice something. Alpha always reduces the top number by 4. You can try it on your calculator. 233 minus 4 will give you 229. You can try it on your calculator. And it always what? Reduces the underneath number by 2, right? It had 92, and look at it now. It has 90. Also, you all notice it was named uranium, but after it gave out alpha, you realize it's no longer uranium. We had to change its name because the amount of protons changed. So it went from being uranium into something totally different. And I believe this guy here is thorium, right? Question 2 is obviously what? Beta. And you notice when something gives out beta, the top number remains the same. Look, 99 here, 99 here. Top number did not change, but the underneath number is supposed to get larger by 1. Remember, we just said that. It was 43, and look at it now. It's 44. All right? Right. And I think number 3 is what? Easy, right? This is also what? Alpha. All right. So here's what I want you all to take down these 3 now. I think that was a good time. And this one was alpha, this one was beta, and this one was alpha again. So all we know for sure is that when this gives out alpha, right, it changes into something different. You could use X, you could use Y. And of course, for alpha, you could use the alpha symbol, or you could put HE. Nobody is going to judge you, right? But it's just easier for me to write alpha. Also, you can write the alpha before the X. The order does not matter. All you know is for sure alpha is 4 on top and 2 underneath. The top number is supposed to decrease by 4. So I believe it's 252. And the underneath number decreases by 2. 101. How much of y'all had that? Right? I know some of y'all did send the answer, but some of y'all may have been too shy to send the full answer. Right now, to be really, really, really complete, you just have to put the word energy after, right? Because alpha particles have a type of energy called kinetic energy, right? But just for today, if you forget how the word energy is okay, it's not really a problem. I just want to make sure you have the calculations part correct, right? Right, and I see some people went to find the actual name of X. Somebody's telling me it's Mendelium, all right? But in the CXC exam, you don't actually have to remember the names. Okay. All right, so that's the answer for number 7. You think you all could try 11 for me? In 11, it's giving off beta decay. So sodium, this type of sodium, let's just assume it's radioactive and it gives off beta. Complete the equation here. Ask yourself, when something gives off beta, will the name change? And of course, and if the name changes, you cannot call it sodium again. Use a different letter to represent it. Decay. So sodium, when something emits beta, it has to change to a different element. You can choose any letter, X or Y or whatever. Beta is 0, -1. Remember, you can also put the letter E here. It's up to you. Like how they have E here, this also represents beta. In beta, the top number remains the same, but the underneath number increases by 1. And of course, beta is a fast moving particle, so it also has energy, and the type of energy would be kinetic energy. For those who didn't submit answers, can you just verify if you had that at least? So let's just quickly start with alpha. If there was a radioactive particle, and well, we know the underneath is A and the top is what? Sorry, that's wrong side. A and Z. If something were to give out alpha, it has to change into a different element, right? Alpha is 4 and 2. The top number always decreases by 4, so you have to put A -4, and the underneath will decrease by what? 2. So it will be Z -2. And of course, well, to be very, very complete, you could put the words energy, right? So that's the decay equation, and that's exactly how the examiner will say it. He will say, hey, write the decay equation for alpha. For beta, if we have a radioactive element, A and Z, if it gives out beta, it will change into a different element. Remember, beta is what? 0 -1, and we also get what? Energy. The top number remains the same, so it will remain A. The underneath number will increase by 1. So it will be Z +1. Gamma is the easiest, right? If you have A and Z, for it to be gamma, most of the times will be an excited nucleus. When it shoots out gamma, it will remain A and Z, and the asterisk disappears, meaning that it is no longer excited, and then it shoots out gamma. Now, for gamma, I don't think you need to write the word energy. Let me explain why. It's kind of redundant, because it's understood that gamma is pure energy. So I would leave out the words energy afterwards, because you'll be saying it twice. Let me know when you finish taking down the decay equations, and afterwards we can move on to something slightly new in radioactivity. Someone had asked if we will be doing half-life. Yes, that's on the slides I have prepared. The question is, would we reach it today or next week? But we will be doing it before the summer is over. The next thing we're going to talk about is how alpha, beta, and gamma move. When I talk about how does it move, let me say we have an atom that shoots out alpha or shoots out beta. Does the alpha move in a straight line? Also, how far does it move? Does it move 5 centimeters? Does it move 10 centimeters? And for beta, if something were to shoot out beta, would it move in a straight line, or would it move in a kind of zigzag pattern? Okay, here's why it's so hard to tell. alpha, beta, and gamma, well, alpha and beta, first of all, are very, very small. In front of you now, it might have a little bit of alpha, it might actually have a little bit of beta, but it's so small, you cannot, your eyes just cannot detect it. So how do we actually see these things if they're so small? Let me give you an analogy. Let's just say there's an invisible man, right? And he's running around the place. He's invisible, so you cannot see him. Anybody has any ideas on the chat of how we could probably see this person move? We want to know if he's running in a straight line. We want to know if he's doing zigzag patterns. So I'm going to listen to some of you. All right, so I'm going to go with the cheapest solution, right? We can either throw paint on him or powder on him so we can make out an image of him. How about this? If we were to spray a whole set of smoke in the room, right? So we have a room and the person's in a room, in a closed room. Let me just ask you. If the person was in a room and we fill it with smoke, try to imagine this. When he is running, do you think he will leave a trail in the room? Like you will see a pattern in the smoke? What do you all think? Right, you might be able to see a pattern, right? So we could also use that concept, a kind of trail. Let him run through something and let him leave a trail. Now imagine this, instead of smoke, what about an artificial cloud? Yes, the same clouds that are in the sky. If we were to make an artificial cloud and have the person run through the cloud, it might leave what? A pattern in the cloud, just like in those cartoons, like when Woody Woodpecker, whichever cartoon you watch, when they run through the clouds, they just leave a little trail. So I want you to look at the next slide now. How much of you all have seen this? Like for those who live close to the airport and whatnot, have you ever seen a plane fly through the atmosphere and it leaves a trail behind it? How much of you all have wondered what that is? I don't know if you're ever bored like me, but and you sat down and you begin to think, what's that behind the plane? Anybody wants to take a guess of what that trail behind the plane is? Most people will get it wrong, but you see this trail behind the plane? That's not smoke, that's not steam. It's so easy to say it's smoke because you imagining a rocket ship, and a rocket ship is what? Leave a trail of smoke. But this is actually this is actually a cloud. But I think I spelled cloud wrong. Oh, geez. Right. It's an artificial man-made cloud. Okay. Now we're not going to go into detail of why this is a cloud. But the point is, whenever something moves through the air, once there's water vapor, the movement through the air just causes the water vapor to condense. And when water vapor condenses, it is formed a cloud, an artificial cloud, a man-made cloud. Which brings us to this. If the plane was moving and we wanted to know the direction of the plane, well, we could just look at the plane and see how the plane is moving. If the plane moving straight, you will see the plane moving straight. If the plane was moving in a zigzag pattern, which we hope it isn't, you will see the plane moving in a zigzag pattern. But if this was an invisible plane, to know how the plane was moving, we can't actually watch the plane. We would watch what? The cloud. So if the cloud is in a straight line, we know the plane is moving in a straight line. If the cloud had a zigzag pattern, we know the plane is also moving in a zigzag pattern. So how do we see alpha, beta, and gamma? Well, it's real simple. We build something called a cloud chamber. And how the cloud chamber works. Long time, when I say long time, about 10 or 20 years ago, for the CXC exams, you had to know how to build a cloud chamber. It was part of the syllabus. Now, you only have to know the basics about a cloud chamber. A cloud chamber is very simple. When alpha, beta, and gamma move through the cloud chamber, it will leave a trail of clouds behind it. So while you cannot see alpha, beta, and gamma, the cloud chamber allows you to see the pattern of clouds left behind it. So if you see a straight line, you know the alpha was moving in a straight line. If it's a curved line, you know the beta was moving in a curved line, right? So take down this note in blue, right? So a cloud chamber is basically a sealed environment, like a room containing either supersaturated water or alcohol vapor. Supersaturated water means it has plenty water vapor, and the slightest movement in it will make a cloud form, right? Let me know when you are finished with everything in the top blue box. All right, so you're probably wondering now, what does alpha, beta, and gamma look like when you put them in a cloud chamber? These are the diagrams here. Let's do, I already explained what ionization was, I think a couple of weeks ago, like what is ionization? And that is simply when you hit something off an atom, an electron, and of course, the charges become what? Imbalanced. As you all remember, alpha is really, really good at ionization. Beta is kind of weak at ionization, and gamma is the weakest at ionization. So in a cloud chamber, this is how the clouds will look. You notice alpha produces straight lines, but the lines are usually less than 5 centimeters long, between a little less than 5. So how does alpha move? It moves in short, straight lines, and you'll need to memorize the value for the examiner. Beta doesn't move in a straight line. You all notice a kind of what? A kind of squiggly line, right? I have the definitions here of exactly how to describe it for the examiner in CX. And gamma, it is be all over the place. It's almost like there isn't a pattern. So the tracks are extremely weak, meaning that you can barely see the clouds, and are dispersed, meaning they're all over the place. So there's no pattern to it. And if they ask you why it is so, because alpha is really good at ionization, beta is weakish at ionization, and gamma is the weakest. So I summarize in front of you, write down everything. If you cannot draw the 3D diagram, just draw a circle like this and just draw straight lines like this. Same thing over here and same thing over here. But the point is, memorize it exactly like how I have it here for the CXA exams. You won't get a simpler definition and well simplification of how it moves in a cloud chamber. Let me know when you are finished. I think about 5 minutes should suffice.